Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. Alright, this is our module number 6, Deep Sequence Modeling, Python Part 2. So in the previous theory lecture, we talked about natural language processing. Actually, these are the slides you can find on my GitHub account. We said that what is NLP, and then we basically said when you want to work with a natural language processing model, it's nothing special. We are using our very own sequence models like RNN, LSTM, and later on transformers, but the input should be transformed, right? So because we know that in, for example, in text, we have to translate those texts into numerical values, and for that we talked about this text vectorization process. We have to standardize it, then tokenize it, make index, and then encode it at the very last. So I assume that you have already watched the theory lecture, or you're already familiar with all these concepts, right? What are different ways of standardization? How do we tokenize things? What is engram? What is bigram? Or for example, what is, I don't know, bag of words and things like that. So I assume that you are already familiar with all these concepts, and now you're ready to apply and replicate the example that we were going through in the theory lecture. In the theory lecture, we talked about this IMDB movie review dataset, and we, at the end of the day, we compared quite a few models with each other, the performance-wise, right? So we looked at the unigram binary, and the performance was 89%, almost 89% in the test set. This is the accuracy. Then we expanded to binary, the Bigram binary, and just to incorporate those local orderings by going from unigram to Bigram, and the performance increased to 90.4%. Then we talked about different version of encoding, TF-IDF. Then so these were the bag of word approach, right? So bag of word approach versus sequence model approach. In the sequence model, we trained actually 4 models. So I'm going to show it in Python. So here's the output of the 3. We looked at the one-hot encoding, which was super inefficient. Then instead of one-hot encoding, we worked with word embedding, one without masking, the other one with masking, right? So, and finally, we also used a pre-trained model and applied to this data set. The pre-trained model using the glove. So here it is. We used the glove scheme. And in this Python notebook, I've used glove scheme, and you'll see that the performance is not quite good. Actually, it's even less than. Let me see. I think the performance is 87%, which is far worse than any of those models that we explore. All right. So we talked about the reasons why this glove scheme didn't work, why the pre-trained word embedding didn't work in this example, and things like that. Please make sure you watch the previous video, and now you're ready to apply these things in Python. Okay, so here's the notebook. Where you can find the notebook is actually go to my GitHub account, Deep Learning, Lectures and Codes, Spring 2023, Module 6, Deep Sequence Modeling. Go to the Python folder. There are 2 files here. Previously, this is Python Part 1, this is Python Part 2. We talked about time series forecasting using RNN and LSTM. And now we want to talk about natural language processing. So without further ado, let's do this. So we go ahead and open this one. I will walk you through this notebook instead of me coding from scratch and then running the models and pausing the video, because again, it's going to take some time and there is no value added for me showing you how to write these codes. You can of course pause the video and then try to replicate it on your own, and etc. So try to focus. I'll try to add some narration on the codes that I think that you might have some maybe difficulty is understanding them. Okay, and just like any other notebook that I've used in this course previously, I'm borrowing a lot from this book called Deep Learning with Python. This is the 2nd edition by Francois Cholet. Of course, the GitHub is publicly available, so you can go ahead and copy from there too. But I basically adopt from that notebook and make lots of annotation to that, right? So there you go. And make sure, and this is our contents, right? So we're gonna pre-process the data, basically transforming the text data, import the data, create the dataset pipeline, train, validation, and test set, TensorFlow pipeline, and then we're gonna do bag of word model versus sequence models, and then finally we're gonna look at the pre-trained word embedding And we are going to make prediction with our winning model, right? Let's say, I think our Bigram binary is going to be the winning model. So we're going to use that model and to make prediction for new reviews. So let's go ahead and do that. Okay, so first things first, we're going to import TensorFlow. You can check out the version by the time you're watching this. It might be different, so just keep track of the version. Importing, actually, I'm not going to use pandas or NumPy or Matplotlib because we're not plotting the validation loss versus epoch. You can go ahead and do that, but I guess by this time in the course, probably you're an expert in doing so. So feel free to do that on your own. So these are the steps that we're going to do by adding the text vectorization layer in TensorFlow, right? So we are, by default, it's using lowercase standardization and removing punctuation. So this is the default values in TensorFlow. You can change them. Tokenization, there are different ways to do that. Then you're going to index them and use one of the encoding method that you're already familiar with, right? So again, depending on what model we use, we change these text vectorization layers, right? But if you have no background in text vectorization, let's see what is it from scratch, right? So there is this layer called text vectorization from TensorFlow Keras layers. And I'm going to go ahead and create this vectorizer. I call it text vectorization. You can call it anything. And this is a layer. It's a TensorFlow layer. And you can change the output. There are many other stuff that you can change, but one of the most important one is output mode, right? If I do output mode is equal to integer, obviously it's going to return the sequence of words and encode them into a bunch of integers. So just for the sake of representation, let's look at a simple example using output mode integer. So when I run this, now this vectorizer has been created, right? So this is our text vectorization. And there's something from the theory lecture that I think you should, it's worth noting one more time. So just keep in mind that to index a vocabulary of a text of corpus, we can go ahead and call it adapt, because we have to say, okay, this is your vectorizer. Now go ahead and fit it, basically fit it to some trained data, right? If you want to do that, you have to do adapt. Then if you want to get access to those computed vocabulary indices, you have to do, not the indices, the vocabularies themselves. You can do .getVocabulary. We're going to see all these things. And just keep in mind that there are two indices that are reserved. 0 is reserved for padding, and 1 is reserved for OOV, out of vocabulary. If there's a vocabulary that it is not in your vocabulary, so it's going to be assigned index 1, and when you retrieve it back to Word, it's going to be unknown, UNK. And yeah, and we already talked about it. What is the standardized? What are the default methods for standardization and tokenization? Okay, so here are the default ones that we didn't need to make any changes here, right? We are using the default values. So if I use the default value for standardization, it's going to use convert to lowercase and remove punctuation. And for the tokenization, it's going to split the string by white space. Okay, so this is what we generated in this object, right? Okay, now imagine I want to fit this vectorizer, right? So remember, this is a layer. I need to pass it some input data and then fit it and basically train it, right? So train might not be a right word, but the idea is that I want to say, okay, this is my train set, this is my text. Let's go ahead and vectorize, use it as my train set, and then I can pass another sentence and see how it works, right? So for example, I'm going to say this is my train set or input data. I call it text data. And the text data can be something like as simple as this, right? The cat sat on the mat. Remember, this is the entire data set that you want to adopt, right? And of course, the entire data set in real world is going to be a lot more, right? So you can, you have thousands or millions or records of data, and then you pass it. You're going to adapt that vectorizer to that train set. And this is what we're going to do for IMDB movie review as well. So we're going to use the train sets in the IMDB dataset. There are thousands of reviews there, and we pass that one to this adapt thing here, basically vectorizing based on that, right? So what I want you to pay attention is that, you see, we have lowercase, or uppercase words, the cat sat on. This is entirely uppercase, and then the mat start with lowercase m and then ends with capital A and T, and we have a bunch of exclamation and etc. So we know that if I use that vectorizer, first things first, it's going to use a standardization, and standardization is going to go ahead and get rid of all these cap letters, get rid of these punctuations and things like that, right? So this is just a very simple example that you want to see what's exactly happening when you're running one line of code in TensorFlow and apply this adapt thing to your train set, right? Something like this is happening. Oh, all right. So now we know that this vectorizer has been adapted to this data set, right? We can go ahead and back out the vocabulary. Remember, we're going to retrieve this computed vocabularies using get vocabulary, right? So if I go ahead and apply it to my vectorizer, these are the available vocabularies inside it, right? And look at that. Well, of course, we are going to have the cat sat on the mat. So these are, of course, the words, right? There are a couple of these. Of course, there's one D here. Sat, on, mat, cat, and these are our two reserved words, right? Remember, index 0 was used for padding, and index 1 was used for OOV, out of vocabulary. So this is index 0, 1, 2, 3, 4, 5, 6. If you want to see those indices for your input data, so you can say TextVectorization, this is your vectorizer, and pass the input data. We usually don't do this, but I just wanted to show you how we can retrieve those numbers again. So I'm going to say text vectorization, text data. This is my input data that the model has been, this vectorizer has been adapted to. If I go ahead and run this, obviously, again, no surprise, remember what is the sentence? The cat sat on the mat, and the index was 2. Cat, the index was the very last one, 6. Sat, the index was, where is it? 3, right? So that's where we're getting these numbers, 2, 6, 3, 4, 2, 5. Okay. All right. So now let's encode a new test data set based on this existing vectorizer, right? So now I have a vectorizer. This is my vectorizer. It's ready. I'm going to go ahead and basically pass it a new sentence. So imagine we have some new input. I'm going to call it, I don't know, something like that. Cat on the table. So something like question mark, right? So remember, this is what the vectorizer has been fit to. The cat sat on the mat, and this is the entire corpus of vocabulary. If anything outside this is going to be treated as OOV, right? So when I say cat on the table, there's no table in the original data set, or the one that the model has been fit to, or the vectorizer has been fit to, right? So I'm going to get an index 1 for this because this is unknown. But everything else is there, and of course the punctuation question mark is going to be removed, right? So let's go ahead and apply that vectorizer to this new input. So I'm going to go ahead and say, okay, so this is the encoded version, right? So we say encoded input, apply this vectorizer to that input, and I can go ahead and print out the encoded input. So let's go ahead and do that. All right, so this is our encoded input, which is basically some indices, numbers 6, 4, 2, 1. Remember, 6 was cat, 4 was on, 2 was the, and then 1, right? This is index 1. If you see what is index 1 here, index 1 is unknown, right? So because again, this table is not part of the vectorization that was adapted to the train set, right? So then that's where the index 1 is coming from. All right, we can also go ahead and translate back this encoded input. We can decode it if you wish, back to vocabularies, right? So how do we do that? I'm going to go ahead and make this is usually the term that we use, vocabulary. This is basically the entire vocabulary that the vectorizer has been adapted to, right? So here, for example, it's going to be something like this: the, sat, on, mat, cat, and then these two paddings and unknown, right? So basically we saw this before, but I'm going to save it in an object called vocabulary. So let's go ahead and do that. Now we want to index to word. So let's remember, the goal is to translate this encoded input back to the sentence based on this vectorizer that we had, right? So I'm going to go ahead and create an index to word dictionary. It's nothing special here. We have a vocabulary. There are two things in it, right? There are the index number and the word itself. So I can put it in a dictionary, enumerate over vocabulary, right? So this is the index: 0 for padding, 1 for unknown, OOV, out of vocabulary, 2 for the, 3 sat, 4 on, 5 mat, 6 cat, and etc. Right? So that's it. This is index to word. Now I'm gonna go ahead and you can do a for loop, you can do a list, list comprehension, whatever you feel more comfortable. I do list comprehension here. We are gonna put together a sentence, of course, space separated. So I'm gonna do space separate dot join. So this is a function in Python to put together a bunch of strings. What are the strings? These are our strings, right? So we say that, okay, go ahead and from this index to word thing, which is a dictionary, remember, take the integer part for these integers in the encoded input, right? So it says that this is the encoded input, and it's going to make sure that this is integer because we're going to loop through it, and then join them together. So basically, it's going to say, okay, 6. What is 6? Cat. What is 4? On. What is 2? The. What is 1? Unknown. Right. So it's going to translate something back. This is the decoded input, right? Cat on the, you don't know what is it, because in the vectorizer in the that was adapted to the train data, in the train data there was no table. All right, so this was very briefly what is text vectorization layer doing in TensorFlow, and basically these steps, right? You can go ahead and play around with all these different versions that we can do for tokenization and etc. So we are going to define all those things in text vectorization. So one big difference between all these 6 or 7 models that we train here is how we vectorize things, right? That's it. So we're going to have a separate text vectorization for every single model, and then the model architecture is pretty much the same. So at least it's the same for all these bag of words, and we are going to use pretty much the same model architecture for these ones as well. Okay, so let's go ahead and do that. All right, let's go to our first model. So there's first model, there are, we have to import the data first. So we prepared the data here. Let me go down, scrolling down. Let's import the IMDB dataset. So from this part onward, I'm not gonna run the cells because it's gonna mess up what I already have run. So look at that, this model has been already the data has been imported. I have saved different models. So these are the callbacks, and we have used the glove scheme for pre-trained model. Okay, so if you are running this code and you're here, probably nothing is there and except the sample data, and then you're going to go ahead and run this line. It's going to import the IMDB dataset. And when you import this one, you will see this folder as a zip file, actually, ICL IMDB. And then there are going to be another unsup dataset in the training folder. We're not going to use that, so make sure you remove that folder by running this line of code. So we're going to remove that folder. You're going to end up with, I don't know, something like this, with a test and train. When you're at this stage, there's no validation. So we're gonna go ahead and make 20% of this data set and import it to a new folder, call it validation set. That way we're gonna have our own test, train, and validation set. So this is what we're gonna do, okay? And if you wanna see what is inside these, for example, data sets, we can go ahead, actually, let me open, maybe the test is a smaller one. Yeah, each folder, there's a negative and positive folder. So these are the positive reviews, those are the negative reviews, and etc. You can go ahead and open it, but remember, these are, I think 20,000, 40,000-ish number of files. So that's why it's taking so long. So we're not going to do it that way. We are going to go ahead and use concatenate function, and then open one of them, for example. We say, okay, from train set, a positive review, let's open this file. And this is the review. Brilliant overacting by Leslie and Warren, best dramatic, and etc., right? So probably this is going to be labeled as positive, right? Because the words are very positive in this review, okay? So this is the length of the review, and etc. I think in the theory lecture we also said that the average length of the review for this dataset is 235-ish words, something like that. Okay. Then the next step is to go ahead and create the pipeline, right? The TensorFlow pipeline. So first we have to create this validation set, right? So as I said, we're going to move 20% of the train data set into the new folder that we will create, call it validation folder, and then something like that, right? So I think this part should be pretty straightforward. I'm gonna fly through it. I actually added some comments here. Hopefully these should help. But I encourage you to go ahead and, because again, I want to keep this video short. And this is kind of not relevant to what we did in the theory lecture. And this is kind of assumption that you're already familiar with these sort of things. It should be pretty straightforward, okay? Well, actually, let me do this one, and then for the rest of the video, just I want you to go ahead and read the comments by yourself. So what are we doing? This is our base directory. The base directory is this main folder, right? And then you're going to go ahead and create a validation directory in, we call it val, and a train directory, which is already there with the train. So we have to create this val, and then the train is already there, okay? We say, okay, there are two folders, right? We can say for categories in these negatives and positives in the train. Go ahead and make directory. We're going to go ahead and make directory validation. We call it val, and then there are two things inside the val. This is a for line. Goes to negative and positive. And then we are going to go ahead and list all those files in the train directory for each positive and negative folder, and then shuffle those files. So you can use any random number. I just wanted to replicate what we had in the textbook, so I use the same seed number. So you can shuffle the files, and then we're going to say, okay, these are the number of text files that we're going to put in the validation folder, 20% of the train size, right? And then again, we're going to look at the very last, this number of files from the train set. This is 20% of the train set, and then use the shoutil function to just move it from train folder, different categories, different file names, to validation folder, different categories and different file names. Okay, so now if you run this, at the end of the day, you will see this folder created with negatives and positives, which is directly copied from train, 20% of the train. All right. Then the next step is to use text dataset from directory. This is a utility. This is a Keras utility to create a batch of dataset, right? This is pretty much the same as what we did in CNN, computer vision. Basically, we did image dataset from directory and created a TensorFlow data pipeline. We're going to do the same thing, exact same thing for text data. So the utility is called text_dataset from. Oh, it's not dictionary, it's directory. Okay, let me actually fix this. The directory, okay. Oopsie. All right, and then we're gonna go ahead and work with batch size 32. And yeah, again, you have seen something pretty much like this in the computer vision. The only difference is that that's it. Instead of image dataset from directory, do text dataset from directory. Then you have to pass the folder name and then the batch size number, right? So we're going to create 3 folders: train dataset, validation dataset, and test datasets, right? Let me actually go ahead and and remember, in each, basically we're going to batch the data, batch size 32, right? So for the train dataset, it's going to go ahead and use the train folder here. For the validation, use the val folder. For the test set, use test folder. If you run this, if you have done everything previously correctly, you should see something like this, right? There are going to be 20,000 files belonging to 2 class in the train set, 5,000 in the validation set. Remember, 20% of that thing we moved. Originally it was 25, and we moved 20% of it, which was 5,000. So now we have 5,000 validation, 20,000 train, and 25,000 test. Okay, for 2 classes. All right, so we can look at some of the outputs shapes, and for example, now remember this thing that we have. This is a TensorFlow dataset. It's a tuple of things, right? So we have input and targets in this, for example, train set, validation set, and test set. And I'm going to look at the first batch data, and that's why we use take is equal to take 1. So take 1 is going to look into the first batch, and in the first batch, we can look at the, for example, input shape, input data type, target shape, target data type. And actually, we are going to look at the first review in the input and the first label in the input, right? So not surprisingly, again, input has 32. These are the size of the input shape, right? 32 different text, different reviews, 32 different labels. So these are 32 text, 32 labels. Labels are 0, 1, so that's integer 32. And imagine this is, not imagine, this is our first review, right? What is it? Things to Come movie review by, here's another wonder-filled science fiction film from a different time and place. It's a film I've seen, blah, blah, blah. But look at the label. The label is 1, so it's a positive review. So probably there should be some good stuff here, right? So this reviewer was pretty happy with the review. Okay. All right, now we get to modeling part. Let me go back to the content. So here's the modeling part. We know that from the theory lecture, we already talked about it, right? We can do 2 types of modeling. You can do treat words as sets, representing group of words as sets. This is a bag of word approach. The other one was sequential modeling approach, right? And here were the main differences between the 2 ones, right? Maybe I think the most important one is the one that I highlighted in yellow, the order. Bag of words, we ignore the orders, right? We can do different encoding or different tokenization methods. For example, we can use engrams to, let's say, synthetically, create some local ordering. If I do ngram n is equal to 2, I'm looking at the cat mad, or no, the cat sat, and things like that. 2 words close to each other, right? But I don't look at the entire ordering in the sequence. Let's say I have a sequence of 200 words. If I use ngram n is equal to 3, I look at the ordering words at most 3 words together, right? So generally we say it ignores the order of words. Because it ignores the order of words, it's going to ignore the context of words as well. This is the bag of word approach. It's going to be super high dimensional, and well, that also depends on the max tokens we use, and etc. And but it's going to be fast, right? Because it's a sparse. There are lots of zeros and probably lots of ones, and then it's going to be faster for training and inference. It is good for tasks that we're doing simple text classification, right? Imagine this is English text, and if I show you an English text, if you're reading a review, sometimes it really doesn't matter the order of the words. You can, no matter where you start or how sporadic you're looking at the words, you can get a sense if it is positive or negative. So that's the idea. And these models actually are powerful. You still use them, so they're still relevant. Versus sequential modeling approach, right? So sequential, of course, the whole point is to capture the order words. Because of that, we can know a sense of context, capture the context of words. Later on in transformers, we're gonna talk about these things a little more. What's the difference, for example, short-term dependencies or short-term memory versus long-term versus very, very long-term, right? So things like that. And it's going to be lower dimensional. It has lower sparsity. Because of that, it's going to be slower training. But it is good for anything that's basically the sequence is important, right? There is a rule of thumb, practical rule of thumb, that later on in the transformer section of the course, I will talk about it. That, for example, when should you use sequential modeling? When should you use bag of words? Okay. All right. So let's go ahead and start the bag of words first. And we have 3 models, right? Single word. So we're going to use unigram. So this is. Let me actually show you from the tokenization layer, right? So we can have word level tokenizing ngram. So this is what we're using. Unigram means just n is equal to 1, right? So unigram, we are using single words with binary encoding. So this is our tokenizer, this is our encoder. The encoder is simply multi-hot encoding. So a good thing about it is that it's going to be the entire input is going to be translated into 1 vector with a dimension of 20,000 here, right? So because this is our max token. So no matter what review you have, it's going to be saved as 1 vector. So this is the biggest advantage of this multi-hot encoding. But when I'm using single word unigrams, simply I'm completely ignoring the orderings, not even the local orders, right? So probably we'll see how it works. So you can go ahead. So do you remember I told you that the main difference between these models is a text vectorization layer, right? So that's it. For the first model, we're going to use max token 20,000 most common words in English, right? And then the output mode is multi-hot. Remember, at the very first of this notebook, I used integer to show you how it looks like, but now we know that what is multi-hot encoding, we're going to work with that, right? So multi-hot encoding is going to go ahead and take your review and make it into one vector with a dimension of 20,000. And basically, if that word was in the 20, what was the, for example, index number of that word in the vector of 20,000, okay, size 20,000. Again, if it is not quite clear, make sure you watch the theory lecture. I gave you some numerical examples there as well using the whiteboard. All right, then let's see. We are going to go ahead and prepare the text vectorization layer that we're going to use later in the data, right? So remember, now I have to go ahead and do you remember at the very beginning of this notebook, we adapted our vectorizer to some trained data? This is exactly what we're doing, right? So this is my text vectorization we just created, right? This is a layer. Now I have to pass some input data. So I'm going to pass some trained data, right? And then we are gonna adapt this vectorizer with this trained data. And later on, we're gonna use that which was already adapted to trained data set, okay? So what are we doing? I'm gonna say, remember this trained DS is a TensorFlow data frame, which has two things, right? The first thing was the inputs. The second thing was the labels. We don't need to have the labels. Labels are 0, 1. So I'm gonna go ahead and only save the text. I call it text only trained data set. I use a mapping function. So map lambda x and y. Again, x and literally input and y. Just go ahead and save the x. That's it. So we're going to discard the labels. Now I'm going to adapt to this text only trained data set. So basically this is a bunch of reviews. Actually, in this case, 20,000. Was it 20,000? I think it was 20,000. I think we had 20,000 files somewhere. Yeah, 20,000 files, right? So we had 20,000 files. It happens to be, it's a coincidence that this 20,000 is the same as our max token number. So don't get confused. 20,000 files, 20,000 reviews there. So basically this is 20,000 reviews in the train set where we're going to adapt our vectorizer. Okay. All right. So then we're going to go ahead and create a new data set with this vectorized data, right? So I will call it binary 1 gram train data set, binary 1 gram validation data set, binary 1 gram test data set, right? So this is pretty straightforward. And again, we're going to use this entire train DS tensor data frame. Again, another map, lambda xy. Now we're going to apply this text vectorizer to all those x's in the train set, and then we needed labels as well. So this is going to be my train data set for the first model. Okay, you can go ahead and run this. You can look at check out the output shape. You know, for example, we have, remember, let's look at the first batch. No, this is take one, batch one, and batch one has 32 reviews, and of course the dimension. Remember, we use this. Each of them are one vector with 2,000 dimension. Now this is a multi-hot encoded thing, so that's where the numbers 32 and 20,000 is coming from. Of course, these are now the reviews are vectorized now, right? So this is the difference. The reviews are float 32 now. It's not a string anymore. The outputs, however, are a bunch of numbers, no labels, 0, 1, 0, 1, 0, 1. You can look at, for example, input number 1. This is your review number 1 vectorized. This is its labeled. So review number 1 vectorized, it's going to become something like this. One single vector with 20,000 dimension, right? And this review was a negative one, I guess. I guess 0 is negative, 1 is positive. All right. Okay, now again, we're done with the vectorization. For everything else is pretty much the same as we did in the last Python lecture video. You can apply LSTM, bidirectional LSTM, I don't know, whatever you want. But remember, this is a bag of words approach, right? If it was sequence modeling approach, I can do RNN, LSTM, and etc. But because this is a bag of word approach, we cannot care less about the ordering, right? And then that means that we're going to use a simple, densely connected layers. That's it. So we're not going to use sequence models like RNN, LSTM here. We're going to use simple DNN, deep neural network. So we can go ahead and define our model. Max token 20,000 using 16 hidden nodes, for example. We can play around with all these numbers, right? This is deep learning. The art part is important, right? It's more an art than science. So these are so many moving parts, so many hyperparameters it can play around with. So defining your input layer, of course, the shape is max token. And we're going to add one dense layer. You can go ahead and add multiple dense layer, but one dense layer with 16 nodes, activation ReLU, and we're going to add a dropout after that. Then conclude this layers with an output layer. Of course, there's going to be one node. Remember, it's a binary thing, right? Is there class negative or positive? For that reason, we're going to do sigmoid activation function and build our model, model input output. All right, so we can go ahead and use RMS prop optimizer. The loss, please make sure it is binary cross entropy. We can go ahead and keep track of accuracy. Again, in this notebook, I did not plot validation accuracy or validation loss versus epoch, but this is something you can easily do, if you watch my previous videos. Okay, we're going to save the best model using callbacks. So we know that when the model has been trained, the best one has been saved with the callback thing, and we can always load that one. Okay, so then we're going to go ahead and look, basically make the model. This is a model coming from this function. It's now a model object. We can look at the summary. Remember, now it is, it has the shape is 20,000 because we use max token 20,000 and we use binary multi-hot encoding. And basically, if I use 16 nodes in the next layer, so 20,000 by 16, 30, 100, 20,000, and adding 16 bias terms, this is why this number of parameters is 320,016. And the very last layer, of course, it's coming from a layer with 16 nodes to a layer with 1. So 16 multiply 1 plus 1, 17. All right, so this is our model. I'm going to use this exact same model for bag of words, model number 1, model number 2, model number 3. So I'm going to use exact same architecture. The difference is using different texture vectorizer, the text vectorization layer. All right, then you can go ahead and train the model. Again, make sure that we have callbacks. So this is our first model. We call it binary 1gram.char. So this is we're going to save the best one only. It's a model checkpoint, right? And we're going to add it to our compile thing later on to keep track of the best model. Let's go ahead and train the model. So we're going to train basically using a train set. And if I remember, I created this, right? We created this up here. So binary 1gram train data set. It was something with labels, right? So it's a vectorized version of the train data set along with the labels. Okay, this is a vectorized version of the validation data set along with the labels and etc. Right, so that's model fit. Again, train, and basically it's going to pass text and labels. And then validation, same story, text and labels, and then 10 epochs, callbacks, model checkpoint. So we run this, it's pretty fast, right? It's pretty fast. And then we get the best model accuracy in the test set was 88.5. So of course, the numbers are going to be slightly different from this slide. So on this slide, because the initialization matrices are different and etc. But here on this slide, it was 89.2. We got into, this is unigram, right? Unigram binary. We got into 88.5. Anyways, so that was our first model. The second model that we synthetically inject some local ordering by looking at two words together, right? So that's why we call Bigram tokenizer, but we're going to use the same encoder. The encoding is multi-hop. So how do we do that? Again, the only difference is the way that the inputs of the text vectorization layer. N-grams is equal to 2, max token 20,000, output multi-hop. So that's it. So that probably this was the only difference, right? Now, the rest is exactly the same. So I'm going to speed up a little bit. So you just make sure that every single time that you have this text vectorizer, you adapt it to this train data set, text only train data set that we created up there. And then we create our data sets that you want to pass to the model. And these data sets are the vectorized version plus the labels. Okay. Then we use the same model. Callback, call it binary 2gram, and then we train it. This is also pretty fast. And then we look at the performance in the test set, 89.8. So this was 90.4. So this was our best performer in the entire among the entire models, and it is the best performer here as well. It's a slightly less, but it's going to be the best performer among these 6 models. All right, so 89.8%, not bad. The third one is we're gonna do, we like this improvement, almost 1% improvement. So it means that this local orders, maybe 2 words together. Here it was 2 words together. I can go ahead and change it to 3 words and see how it works. I encourage you to do that. And if you get a better number of words in terms of test accuracy. But it seems that it works, so I'm gonna stick to that. But I changed the encoding method, going from multi-hot encoding to TF-IDF. So TF-IDF, as we talked about in the lecture video, just keep track, make sure it's a different version of encoding. In practice, for many data sets, it works. It simply increased the performance in the test set by 1% on average. But here, it simply didn't work for some reason that we already covered in the lecture video. Okay, then, so how do we do that? Everything is the same. We are using, just n-gram is equal to 2, max token 20,000. This is a new thing. Instead of multi-hot, we just do TF-IDF. Okay, so with the TF-IDF, exactly the same thing. Let's go ahead and train the model and save the best one as TF-IDF 2 grams. If you do that, if you look at the folder, we're gonna build these things, right? These Keras files. Binary, 1 gram, binary, 2 gram, and then etc. So by the time that you're running this code, so you're generating these things one by one. Okay. And this is going to be trained fast as well. Because again, this is, we're looking at bag of words approach. It is faster because it is, remember this slide, the training time is going to be a lot faster. Let me see, yeah, this one. Because there's high sparsity in the data, right? Lots of zeros, ones. Dimensionality was 20,000. Yes, it's large, but there are lots of 0, 1s. And it's going to be faster. And that's one reason. Another reason is that we are using a DNN model, deep neural network. Actually, here it's not deep at all. There's only one hidden layer. And it's going to be faster compared to sequence models like RNN and LSTM. So that's why, in general, this bag of word approach is going to be a lot faster, actually. Compared to our sequence modeling approach. So with the TF-IDF, we get the test accuracy 88.8. So it's not, it's quite competitive, but it's not as good as the Bigrams, Bigram binary encoding. Okay, so that was it. That was the bag of word approach. So just like what we did we showed in the theory lecture, it seems that in the bag of word approach, the binary bigram is the winner. Okay, so 90.4, and here was 89.8, I guess. Okay, now the second type of models that we cover is sequence model approach, right? So for the sequence model approach, the whole motivation is that, okay, let's build models that are aware to the orders, right? To the word orders. Maybe in this movie review, ordering matters, right? At the end of the day, we'll see that we don't need to be worried about the long history of the orders, but it seems that local ordering was important, right? Regardless, let's see how it works. So we are going to go ahead. The first part, this thing is going to be pretty much the same, but there's this new thing called max length. So the number of max tokens is the same, 20,000, right? But max length is, now we are going to truncate the maximum length of reviews, right? So imagine if you have a review that has a length of 1,000, we're going to look at the first 600 words. This is not necessarily a good thing, but we have to keep it short because, again, you want to pass the LSTM or RNN. So those models are computationally heavy already. So we have to truncate this max length of the review or input, right? So, and the number of 600 is, of course, it's not arbitrary. In this data set, the average length of the review was 230, and it seems that only 5% of the data goes beyond 600 words, which is maybe just 5%, which is reasonable, right? You can go ahead and increase it to 700 and see how the model performs. And actually, this might be one reason why this sequence modeling is not getting to a good performance as the bag of words models, right? So maybe you can go ahead and increase this one with, of course, sacrificing some of your computation time. Okay, so that just be aware. This is a new thing in sequence modeling compared to bag of words. Then we are going to go ahead and this is our text vectorization layer, right? Max token, again, 20,000. Output mode, we're gonna, it's gonna be integer, right? 0, 1, 0, 1s, and then we're gonna, not 0, 1s, so these are the integer, then we're gonna vectorize them later on, right? And for the output sequence length, we are gonna use 600. So this is number 600. So this is our text vectorization layer, right? Then, so we're gonna adapt it to the train set. Remember the text only version of the train set, we don't need to have the Y's. And then I think we have seen these things before, right? Let me go ahead and close this one. I'm gonna say, this is integer train data set. We are gonna apply this map to, look at that. This is a vectorized version of the X plus the labels, right? So this is integer train, integer validation, integer test, right? So this number of parallels is equal to 4. It's just, it's gonna do some, take advantage of the GPU and then parallel processing. You can go ahead and increase or decrease it. Okay, so now we have a bunch of indices, right? The next step is to just try to encode them, right? So if I go back to the theory lecture, basically show you where we are kind of here, right? So we have a bunch of indices now. So the rest is how we can encode them. I can do one-hot encoding, or I can do word embedding, or I can, for example, do pre-trained models, right? Use pre-trained word embedding. So we're going to do all the three here. So the first one, which is obviously the most inefficient one, is doing one-hot encoding, right? So I can go ahead and take these things and then one-hot encode them, and then we are ready to pass that encoded thing to the neural network and then call it our model. Okay, so this is actually the model that we're putting together. So this input layer, and then we are going to add this embedding layer, and it's one hot encoded version of the inputs, and we're going to pass these inputs to the model later on. Okay, the depth is going to be max token, right? So remember, this is the 20,000. We're one hot encoding those 20,000 words. All right, so then let's build our sequential model. So we're going to stack, are we stacking? No, we're using one bidirectional layers here. So this is a bidirectional LSTM with 32 recurrent cells, and we are going to just put it on top of the embedding layer, right? Then we can go ahead and use dropout for 50%. This is our final output layer. It's a dense layer with one node and activation sigmoid. Everything else is the same here. You can look at the model summary and create a model checkpoint, call it one hot bidirectional LSTM, and then run this. And of course, you see the number of parameters is going to be a lot larger. I think, yeah, in the previous model, the bag of words was 320,000. Now we're dealing with 5 million-ish number of parameters, right? So one thing that you should just consider is to running these models for longer, more than 10 epochs. Especially we have this dropout layer, so we need to run it for longer, but just for the sake of, I don't know, maybe visualization, and then for this practice, I just run it to 10 epochs. You can go ahead and try it more, but this is time consuming. It's going to take time. So each iteration is going to take 3 minutes, right? So this is long. And yeah, you can go ahead and train the model, look at the performance in a test set. Again, the very simple version of this model is giving us, the bidirectional LSTM is giving us 86.8. It's not as good as even the binary Bigram thing, the bag of words. That was close to 90%. But take it with a grain of salt. So maybe we should let it run for longer. Maybe we should, we can, because we can always improve this simple LSTM. We talked about it in the previous Python part as well. We can stack a bunch of these layers. We can go ahead and add the recurrent dropout. So there are different ways to actually improve this simple LSTM. But just here, you see that the performance of the simple LSTM was not as good as the bag of words. All right, 86.8. Then, and of course, this was the most inefficient one. Why should we do one hot encoding if we can do word embedding, right? So we're going to apply the word embedding here, and let me see. Okay, actually, if you want to know what is word embedding, maybe here I quickly talk about it, but double check the lecture video, the theory lecture that we covered last time for NLP. But basically the idea is that, so this is a one hot encoding versus word embedding. Word embedding is the dense, low-dimensional, structured representations that are learned from the data. At the end of the day, you're going to end up with a bunch of words. So these word vectors, these word vectors are pretty interpretable, right? So for example, we can have a word vector for gender. We can have for verb tense. We can have one for in country capital. Then if I apply this word vector to a word king, I get queen. If I pass it to man, I get woman. If I pass it to boy, I get girl, and things like that. So, and of course the dimensionality is going to be a lot less. So usually we go with 256, 128, and etc. Or I think in this case we're going to go with 100. And yeah, so this is the idea of word embedding. Instead of working with 20,000 one-hot encoded vector, we're going to work with 100 dimension. It's more concise and it is learned from the data. So this is interesting. So this word vector itself is learned from the data. Okay. All right. So this is the idea of word embedding. So everything is pretty much the same except the embedding layer that we added after the input layer. So this is the embedding. So we say embedded layers.embedding and input dimension 20,000, output dimension 256. Okay, sorry, I was wrong. It was not 100, it's 256. Actually, here we go. We define it here. And this is our embedding layer, right? 256. Actually, I can go ahead and add this embedding layer here, but I just created it one more time. Just be aware. All right. So again, the same bidirectional LSTM with 32 recurrent nodes, 50% dropout, pretty much everything the same. Again, 5 million-ish parameters, not surprised here because the structure is the same, architecture is the same, right? And we use the model fit. This is a lot faster, but still it's a lot slower compared to 2 seconds or 3 seconds per iteration in the bag of words approach, right? What do we get in terms of model performance in the test sets? 86.9. So this word embedding is quite comparable to one-hot encoding, and it was faster, right? We go from 3 minutes to almost 1 minute. And the reason that, so probably here, again, we work with a very lower dimensional embedding thing, which is going to speed up the process. Okay. Okay, so the last one is it the last? Okay, so the last one, oh, no, I'm going to talk about the word embedding with mask, right? So let's actually pause for a second here and tell you what's going on. Okay, so what we did previously here, as you can see, we didn't talk about masking things at all, right? So, but here we want to change that. So everything is exactly the same, but I add this mask 0 is equal to true. So this is the only difference between this model and the previous one. But what is it? So imagine, do you remember we had a max sequence length of 600? So we're going to accept the first 600 words of a review. And what if a review has only, 10 words? This movie is awesome. I loved it. Something like that, 6 words, 7 words, right? We have an input with the size max input length of 600. So it means that the first 7 ones are going to be some indices and etc. The rest is all going to be 0. Okay. And well, 0 or some index, right? So then the thing is that if I use one of these bidirectional LSTMs, it's going to process the data from left to right or right to left, right? Then the problem is that for lots of those, so again, remember the max input length is 600, and then only the 7 in this have some values in it. Everything else is just 0. And if we're looking at another direction from right to left, there's so many inputs in our sequence, which is kind of nonsense, right? And we're passing those things to the recurrent cells again and again and again for 500 something times. So it's going to make those weights all biased, right? So how can we ignore that? We have to tell the network somehow that if you see those zeros, just ignore them, right? So this is what the mask 0 is equal to true is going to do for us. So then if you do that, again, with the exact same setup, the performance and we train it with the performance in the test set is going to be 87.6. Actually, it increased, right? So because it was 86.9, actually it increased by almost 1%, which is, or 0.9%, which is quite good, right? So yeah, just be aware that this is what we were doing. And let me see what else. Yeah, we use LSTM. Yeah, actually we're using LSTM, and sorry, I'm noticing something here. This is called embedding bidirectional GRU with masking. This is not GRU, so I'm copying it from the notebook, but probably something is missing there. So this is LSTM, but again, just we're keeping track of the name of the models. I'm quite sure that you can do it on your own too. All right, so that's it. This is the let's say bag of word approach versus sequential modeling. One last thing that we can do is word embedding, but not learn from our data. Let's work with word embeddings that have been, pre-trained on huge data sets, huge corpus of data, right? So there are two schemes that we talked about them in the theory lecture, word2vec and glove. So here we're going to work with the glove, right? So let's look at the glove scheme for word embedding. Again, the idea is that let's not learn those word embeddings from your data set. What if your data set is small? You want to learn those word embeddings from a very large data set, from a model that has been trained on a very large data set, right? So that's the idea. This is something analogous to transfer learning that we covered in computer vision. All right, so for glove, so here's the website. These are the one that we're going to use. Actually, this is what the textbook used. I'm going to stick to that one as well. So we can go ahead and download the data set from this website, and then we're going to unzip this glove.6b.zip. So if you go to the files, because it reset. Okay, it's there. Sorry, I thought that we lost them. So as you can see, we have different versions of this glove. And then we're going to work with one of them actually. Let me actually show you the documentation and talk about it a little more. Okay, so let's go to this glove website. So as you can see, this is an unsupervised learning algorithm for obtaining vector representation, basically our word embedding vectors, right? And we can download these pre-trained word embedding vectors. There are different versions of them. And then depending on what dataset that they have been trained on and how many embedding dimensions we can have and things like that, we can work with any of them. For example, if you're, dealing with datasets from Twitter, probably you would be better off using this one. But here we're going to use this one. We're going to use glove.6b. And then if you look at that, what is this? This is 6 billion tokens, 400 unique words. And these are, and it is available with embedding dimension of 50, 100, 200, and 300, right? And this is 822 megabytes, right? So this is maybe the lightest one, I guess. I assume, yes, yeah. And then if you want more richer word embedding, probably you can work with it. So the first one, by the way, was basically the data has been extracted from Wikipedia and GigaWords, right? Common Crawl, of course, this is richer, right? So, but it's going to be larger, right? 1.75 gigabytes. 42 billion tokens, 1.9 million vocabularies, and etc. So it's 300 dimension only, and because these are super large data sets, right? And then the next one is 840 billion tokens. So this is insanely large, right? With 2.2 million unique vocabularies. And yeah, 300 dimensions. So we go from that super huge, gigantic dimension to only 300. This is neat, right? This is pretty impressive. But regardless, so we're gonna, let me just keep it short. We're gonna work with this one. So we know that our data set has been trained on Wikipedia and GigaWords, 6 billion tokens, 400 unique vocabularies, and we're going to work with this 100 dimension for the embedding output. Okay, so let's go back, and that's why we're going to import this one. Remember, we're going to download this one, unzip it. So this was 822 megabytes, right? Then our job is to parse this glove word embedding file, right? So again, this is I want you to read the comments. It should be pretty straightforward. Basically, we're going to work with this one. You see, when you unzip the glove .6b, you're going to get these things, and we're going to work with the one with the dimension of embedding 100. So okay, this is the one that we're going to work with, right? It's 331 megabytes. It's a big file. And then we are going to go ahead. So our job here is basically go ahead and index those things. Basically, we want to index those word embedding, right? So this is what we're going to create. We're going to create a dictionary call it embedding index. Because guys, remember, at the end of the day, we know that this dataset that we're importing has 400,000 unique words, and these are word vectors, and we're going to index them. So this is in a nutshell what we're doing in this cell, right? So that's why I'm going to work with my own embedding index dictionary. So inside this embedding index dictionary, at the end of the day, we're going to have something like this. For each word, give me a string of coefficients, right? So, and basically, I'm going to translate them from word vectors to some numbers. And then we're going to pass these numbers to our embedding layers, and that's it. Okay. So again, I'll leave this up to you. This is pretty straightforward. So make sure that you read through the comments, and it should be straightforward. And maybe write in the comments that if it is not clear, I can definitely help. All right. So again, I added some text here. By loading pre-trained word vectors, you can avoid the need to train your own word embedding from scratch, right? So this is the whole point of doing word embedding. So and then. This in the next block of cell, we are going to basically go ahead and generate our embedding matrix, and we're going to use that embedding matrix as the initial weights. Let me go ahead and do that as the initial weights in the embedding layers, right? So remember guys, I have an embedding layer, right? Inside that embedding layer, I need some weights for the word vectors. Those weights could be either learned from the data or it could be borrowed from a pre-trained model. This is what we're doing. So we created this embedding, let's say embedding index. Now we're going to create this matrix out of that embedding index, and then we pass that matrix to the embedding layer. That's it. This is what we're doing. Okay. So we can, again, because this is the one that you want to work with. So we're going to say embedding dimension 100, and we have done this before. You don't need to do it again, but I just wanted to put it here just to re-emphasize. This is our vocabulary. Right, TextVectorizing get vocabulary, and then we can go ahead and basically map each token in the vocabulary into an integer index. So we're going to do it with a dictionary, right? So basically we are putting together, we are making a tuple of vocabulary and basically the index of the words in that vocabulary, and then make it a dictionary. So this is your word index. Then let's go ahead and create this embedding matrix. So we're going to start with the all zeros with the dimension of max token and embedding dimension. Remember, the max token was 20,000 and embedding dimension was 100, right? So this is what we're doing. So 20,000 and 100. And then we're going to say that basically if the word is in the embedding index that we borrowed from a pre-trained model, go ahead and assign the index to this embedding matrix that you're creating, right? So we say that, okay, embedding vector, and then pass that embedding vector to embedding matrix, okay? All right, so this is how we can go ahead and create our own embedding matrix. This is the initial matrix that we will pass to the embedding layer, right? From a pre-trained model, right? So the rest should be pretty straightforward. Now it's time to create the embedding layer, right? So, and we add it after the input layer and before the bidirectional layer. So this is our embedding layer. So basically we are doing what? Max token 20,000, embedding dimension 100. This is why we did this whole thing in the previous two cells, right? Embeddings, initializers. So we're going to say use this matrix that we just created as the initial weights for our embedding layers. So we're not going to initialize them, for example, with 0, then later on should be learned from the data. We say that use this, which has been pre-trained, and then when you use that, do not make any updates, right? So trainable, false. Don't make any updates. Use those things and then call it a day. This is your word embedding vector. We're going to use those things and then go to the next layer. Mask 0, again, we're going to use mask 0 is equal to true, okay? We're going to treat zeros as spatial padding. Okay, so input layer, embedding layer that we just put together, then add our bidirectional layers, right? So for example, we can do LSTM32 recurrent cells, dropout, output layer, and the rest is pretty much the same. All right, so we can go ahead and run this, and with look at that. There are 2 million parameters, and the trainables are only 34,000. Okay, simply because we turn those embedding vector weights to be not trainable. That's it. We can go ahead and run it. Of course, it's going to be faster compared to the previous to the sequence models because the word embedding part is done. Basically it's imported from somewhere else. The performance is 87. This is the worst, right? So if you look at the performance among the, here. Actually, I didn't list it here. It's almost, if not the worst, it's one of the worst, right? Okay, so why this word embedding didn't help us to improve the performance in the test set? Because the IMDB dataset was rich enough, right? So that's the idea. The train set has 20,000 reviews, and with that 20,000 reviews, if we go ahead and learn the word embeddings from the data, it did a decent job. So we didn't make any improvement over that by using a pre-trained word embedding. Using pre-trained models, pre-trained word embeddings usually work for the dataset, which is small. So imagine you have, 10 reviews, and you want to make a good model out of that. So you're going to work with word embeddings, right? Well, 10 was so exaggerated. Maybe 100, 500, something like that, right? You can go ahead and leverage the more richer word embeddings from Glove or Word2Vec schemes. So that's the idea. Now here it didn't work simply because our original data set was rich enough and the word embeddings learned from the data was good enough. So that worked. Okay, now let's say we have 6 or 7 different models and we pick the winner. Here the winner was binary Bigram, Bigram with binary encoding. And we want to make predictions using that winning model. So I'm going to go ahead and import it one more time. Right? So this is model Keras, load model binary bigram.keras, and then we're going to add our text vectorization layer. So remember Bigram, 20,000 tokens, binary output, right? Multi-hot output. Then we are going to make sure that we adapt this because again, we reset this text vectorization, right? You can use different names throughout the notebooks, but there's no point of doing that, because you're just wasting some memory. We can replace these things, right? And so if you do that, you have to make sure that you adapted it one more time. So we adapted to the train set, the text only of the train set. Now it's ready. Now I have a model. The text vectorization is there. I can go ahead and basically get a new movie review, or 2 in this case. Here's a list of your new reviews. So I have a list of 2. So one with good review and one with bad review. The first review is, that was an excellent movie. I loved it. So obviously it's a positive one. And the bad one is, this was worst movie ever. So I hated it, right? So no surprise, the model should be able to label this one 1, this one 0, right? So this is your input text. We're going to vectorize it based on this text vectorization, basically vectorizer that we just created, right? Based on our best model. Now the output is going to be something like this, model.predict. So I pass this vectorized version of the input. And there are 2 things, right? And then print out the model predictions. If you run this line, you'll see the output. So the first review, there's 89% probability that it's positive. The second one, there is only 8.9% probability that it's positive. So this is our positive review. This is our negative review. All right, that was pretty much it. This is everything, in my opinion, that you needed to know for now for natural language processing. Can we improve the performance of the models? Of course, that's the job of transformers. So this is a topic for our next module. So until the next one, take care.